Hello, this is Jennifer Martinez, and today we're going to look at section 2.5, Modeling with Linear Functions. This section is about bringing together everything we've learned about linear functions and applying it to different kinds of real situations. First, a quick reminder of the three ways of writing linear equations. The first way we learned was slope-intercept form. Here it is right here. What is the slope? The slope is in front of the x, so it's m. And the y-intercept is the constant, it's b. Then we learned point slope form. So you don't need just the intercept, you can use any point, but then you have this formula. The slope is still m in front of the x, but it contains the point x naught, y naught. Sometimes I do x1, y1. And the last one is called standard form. We haven't talked much about this, a little bit in the last section, but we will see it a little bit more. It is useful, though, for describing situations. And what is standard form? Standard form is when you put the x and the y all on one side and the constant on the other. So like in the slope-intercept form of here, if we move that x on this side, it would be in standard form. So I'm just going to add something here. Where the a, b, and c are constants, just to see an example of this. Like maybe you had 2x plus 3y equals 6. That would be an example of standard form. Okay, let's look at example 1. Example 1 says the monthly cost of a certain Google Fi wireless data plan is $17 plus $10 per gigabyte, GB, of data. Write a formula C for the monthly cost when you use D amount of gigabytes, which is what I think that is. So let's let use some red. So I'm going to let D use the amount of gigabytes used, the amount of gigabytes of data used. It's a little better. And what we want to know, C, what is the cost? This is the monthly cost. So what is a formula for C? C is going to be, it says, let's read it again. The cost is $17, so 17 plus $10 for every gigabyte of data used. So we've done this before, but 10 is the slope, isn't it? 17 is the initial plan, 10 is the slope. Oop. So we want to just add that D there, and it does make sense because when D is 1, it would be 10. When D is 2, it's 20. It's $10 for each amount of gigabytes we use. What form is that? That is in the slope-intercept form. And that is the answer. Example 2. A roofer charges $7,000 to replace 500 square foot roof. For every additional square foot over 500, they charge $6 more. Write a formula C, the cost of replacing an A square foot roof. Okay, so what's the cost? So this would be the initial cost still. So that would, the charger $700 or 7,000. And this is still the slope. But now, whoops, should put a 6 there. Charges $6 for each additional, so that is a slope, right? It's a rate. But now instead of just doing X, we have this extra 500, and that is going to be for every additional. So if you remember the meaning of this inside, that this would be the 7,000. Well, let me just write it and then we'll talk about it. So at 500, it would be exactly 7,000. So that's like its own little y-intercept. It's at a point, right? So it is the initial amount at the 500, right? And that's why I called it x1, y1 instead of x0, y0 to not confuse that. But it is the initial amount there. And each additional, like at 600, or sorry, 501, it costs $6. So that is using the point slope form. So we have an example of each of those. Let's look at example 3. If you have $20 to spend on fruit for your family for the week, apples cost $1.50 per pound and bananas cost 40 cents a pound. Write an equation about A and B, the amount of apples and the amount of bananas that you have. So this one is kind of different. You're almost like you're given two rates there, aren't you? And you are not given an initial amount. Well, that's like a total amount, isn't it? So what are we going to do? So again, I'm just going to start with the unknowns. A is the amount of apples that you buy, and B is the amount of bananas you buy. Okay. So you have $20 to spend on fruit, and that is a total. So the total is $20 that you have to spend. So that is going to be the amount of apples. Oh, cost. That's $1. So put $1 there. Cost of apples plus cost of fruit. Cost of bananas. So $20 is the cost of apples plus the cost of bananas. So let's put a 20 here. What is the cost of apples? So apples cost $1.50 each, and we bought A of them. So I'm going to use that same idea as up there. It looks like the slope, and it is for the apples. But then we have this other thing about bananas. So I'm going to do the same idea. I'm going to add this. Oops, that's an A, not an X, though an X would be a fine variable if you want to use it. Okay, the bananas are only 40 cents a pound. So that's 40 cents. If you bought one, it'd just be 40 cents, but we bought B of them. So we multiply those together. That is an example. We could rewrite it, by the way. A plus 0.4 B. You don't need those extra zeros if you don't want them. And we're going to say that's equal. Put the 20 on the right side, though it doesn't matter. Either answer is fine. And this is an example of standard form. Notice how we could get this into y-intercept form if we solve for B, right? Or in our case with x's and y's, if we let this be x and this would be y, we would solve for y. You can see that's an example of standard form. And notice how the A and the B and the C are constant. So that's what's new in this section. The other thing that we're going to talk about is visualizing when something is linear. And that's what example 4 is. How can you tell if a table is linear? Well, we know a table is linear if it represents a line. Linear is just, if you remember from before, a fancy way of saying whether the function is a line, or when a function is a line, the slope is the same no matter what 2 points you pick, which means that the rate of change never, right, it is constant, right? And that's why they came up with the name linear, because if it's not linear, that slope would be different. So let's just look at the slope. If you remember, what is the slope for part A? It's the change of y over the change of x. So if I take the first 2 points and I do right? Or let me just write it out. It's y2 minus y1 over x2 minus x1. So I'm going to take that 180, we've done this before, 200, and then the new minus old, Okay, so that is, we'll call it the first set. Well, if I look at the second set, maybe these two. Do I get the same thing? Well, let's just try it. The same formula, 160 minus 180 all over 10 minus 5, negative 20 over 5. It looks like it is. In reality, you really need to check every single point, but if you notice, right, this is always going to be a negative 20, right? Going down 20, down 20, down 20, down 20, down 20. The bottom is always going to be 5, up 5, up 5, up 5. So yes. Yes, part A is yes. It could represent a linear function. Let's look at B over here. Okay, so what is the first one? M1. Guess I'll move B a little bit lower. Okay, so looks like the same thing, doesn't it? It's going to be negative 4 at the same points. The change of y over the change of x. Still y2 minus y1 over x2 minus x1, so it's exactly the same, 180 minus 200 all over 5 minus 0, negative 20 over 5, which is negative 4. M2, is that the same? Well, the numerator looks the same. That's the second one. 160 minus 180. It's exactly what we had before, but the denominator now is 15 minus 5. So we get negative 20 over 10. So M1 does not equal M2, so not linear. No. Let me add that to this one. M1 equaled M2, so linear. So the answer was yes. So you need to check the slopes are the same, really for all points. But if there is a pattern, you can stop. I realized I forgot one step for part A. Part B, there's really, I don't know the formula is, but if it is linear for part A, I could have figured out what the formula was, right? I could have used y equals mx plus b or b plus mx, whatever one you feel more comfortable with. Because what is the m? We just found the m, negative 4x. And the b is the initial amount, so that's right there, plus 200. So it did say, give a formula if you could. By the way, part B, since it's not linear, we do not know the formula for that yet. So now I would like you to try exercise 1. Could the table below represent a linear function? And if it could, right, give a formula for it. So pause it, try it, and then come back to look at. Here's the solution to exercise 1. You can see the first one is not linear because M1 is not even equal to M2. The second one is yes. I realize there's not a pattern. They look different, but if you try each one, so I did, they all are the same. And here's the formula.